through all of partial fractions today. Because looking at the calendar, we have a couple partial pieces. But I think Friday is preferable to the day after a 3-day weekend. And then that's Museum of Tolerance, we can't do that. And then this, we're like a whole week behind, so no. See what I mean? Like, I don't want to set you guys up for failure. That would not be a good idea. So we need to get through this today. Now, nice thing is, we're just playing with algebra. And we're going to see some cool tricks, because don't you guys like shortcuts?
Yes.
But we gotta get the main idea before we can look at the shortcuts, and then we can figure out for each problem what's the best plan of attack. Does that make sense? Partial fractions. We have a fraction that's been all put together. Common denominator, if that's a verb, put together. We're trying to break it apart. First step, factor the denominator. Make a partial fraction for each denominator set equal to the whole thing. Could be 2, could be 3, could be 4, usually 2, sometimes 3. Okay? If the denominator is a linear factor, like these, why are they linear?
First power.
First power. If they're linear, they have an unknown constant alone on top. If they're quadratic, we'll see it and we'll learn how to deal with it. We saw on Friday that once you have the entire fraction factored with its partial fractions, what do we do to both sides? Multiply by the common denominator. Multiply by the whole shebang. And if you noticed on Friday, I wrote it 1, 2, 3 times, so I could clearly see that whole thing cancels. That one cancels, 1 is left. That one cancels, 1 is left. And then I said, in the directions, solve with a system. But then if we look at this, we're like, it's only one equation. How can there be a system when there's only one equation?
Make up stuff.
Huh? Not make up stuff. It's more like look and see what you have. On the left-hand side, don't we have an x term and a constant? On the right-hand side, we have x terms and constant terms. Terms with x's and terms without x's. Question, can 2 x terms ever make a constant? Not very well. Can constant terms ever randomly turn into an x? No. So what I said was, you know what, we have 2 unknowns, and we have 2 categories of types of terms. We have the x terms, which I went ahead and set the 1x on the left side equals ax plus bx. If we divide everybody by x, or factor out and then divide, can't we just say 1 equals a plus b? The only way to get 1x is for ax plus bx to combine. The a plus b has to somehow equal the 1. And then down here, the constants, well, the 7 didn't have an x, the 2a didn't have an x, and the negative 3b doesn't have an x. I said on Friday, last thing, I said, hey, there's a system. Right? Now you guys get to choose. Matrix, elimination, substitution. What do you want to do?
Elimination.
Matrix. How about elimination?
Yes.
I heard that one. Can I multiply him by negative 2? So I have, let me erase the underline. So then just rewrite it underneath this guy. So I have negative 2 equals negative 2a minus 2b. Are we good? 5 equals negative 6b. Therefore, b equals... Pause, you multiplied. What's negative 3 minus 2? There you go. Is that a little better? Divide. B equals? There's 1. And once I have 1, what can I do? Back substitute. Is that an easy place to back substitute? 1 equals a minus 1, so a equals 2. And that's a. Well, pause. Remember, the point was to get the partial fractions, and we had them ready, but what were we missing? The numerators. What we just find? The numerators. So then we can say at the end of the day, hey, guess what? X plus 7, that big old rational expression, could be split up into 2 simpler parts where the a, which is 2, is over the x minus 3, and the b, which is negative 1, is over the x plus 2. Kiddos, look at the very beginning of your notes. Was that the statement that we had? So how do you get from beginning to end? How do you get from rational expression to its partial fractions? Factor, make little partial fractions for each factor. Need to solve for the unknowns, multiply everybody by the common denominator, cancel out all those denominators, get an expression, separate each type of term to get different equations, put the equations together, substitution, elimination, if worse comes to worse, matrices, done. So, yeah. You got it?
Yeah.
Okay. You want to see a trick?
Yes.
That works on the simplest types. Oh, well, it makes the simplest types shorter. We'll take it, right? Something called the thumb trick, or as BC learned this year, the Oliver Heaviside trick. Although Heaviside was not heavy, he's quite thin actually, but that was his name. You guys will be able to use your thumbs. I'll be using my whole palm. But thumb trick. It starts the same. Ask yourself the question, do I need to polynomially divide? Wait a minute, we didn't divide in the last one. Isn't there something about divisional? When do we do division? When the numerator has a higher degree or a bigger power than the denominator. Do I need to divide? No. Top doesn't win. Bottom does. Okay, so no division. So then what do? I factor.
3 and 1.
Yep. X plus 3, x plus 1. Good job, Don. So how many partial fractions do I make? 1 for each denominator, or I should say 1 for each factor. Are they linear? This trick only works for linear. Linear, unknown A, unknown B. According to the last example, what would we say we do to both sides? Multiply by these two guys, right? Multiply them there, both of them there, and both of them there. Cancel out, group the x's, group the numbers. When we do that, this guy always ends up with the other guy as a factor. This guy ends up with the other guy as a factor because the one denominator that does have cancels down. So this guy named Heaviside basically figured out, hey, if it's always going to happen that way when you have linear factors, and at this point, if you could plug in this guy's 0, x plus 2, what would make him 0? Negative 2. If I plugged in negative 2 here and here and here, this still has to be equal. This has to be equal for any value of x. Why would we want to plug in negative 2? Well, wouldn't that just go away? And then wouldn't you have a negative 2 here in the other factor, and a negative 2 here, and maybe b would be easy to solve for? Heaviside said, you know what, let me make this into into a cool trick, a shortcut trick, and here's a shortcut trick. When you with your thumb, because it should be able to cover it, me with my, not thumb, my palm, I want you to just put your hand on on the left-hand side, on one of the factors. Put your hand or your thumb on one of the factors, literally, covering it. Okay, now look at your thumb as to what the factor is. Can we all cover the x plus 3, is that okay? Covering the x plus 3, okay? Now hold on, pause, look under your thumb or your palm. X plus 3, what would the 0 of this guy be?
Negative.
Okay, now cover him again. He's covered, right?
Yeah.
Keep him covered. What's left? X minus 2 and x plus 1. Okay? For the x plus 3 term, why am I saying that? Because he's the one covering. We can plug negative 3 into the other x spots, and guess who we will find? A. What's negative 3 minus 2?
5.
Negative 5. Over. What's negative 3 plus 1? Negative 2. Guess what we just found? A. We'll go back and double check with the other one, but ready? Hold on, your guys' turn. Now we need to cover the other guy. Why? Because we need his. Tell me what to do. I'm covering the x plus 1. Now what? Plug in negative 1.
Negative 3.
So negative 1 minus 2 is negative 3. And then negative 1 plus 3.
2.
So I have negative 3 over 2. Double check. Negative 1 minus 2 is negative 3. Negative 1 plus 3 is 2. Negative 3 over 2. Now, they might write it a little differently. In that complex fraction, well, first of all, negative over a negative is a positive, right? Is that okay? Then couldn't we multiply top and bottom by 2? Like 2 over 1. I would end up with 5 over the 2 joins the denominator. That's how the book will normally write it. It won't write 5 halves over. It'll write 5 over 2 times x plus 3. So can you guys figure out how is this one going to get rewritten?
Wait, what is it? 2.
Because when you multiply top and bottom, the 2 just joins, and this one it's 2 over 1. It's a whole 2. That's just my complex fraction trick. Multiplying the top and bottom by the little stuck guy. If you don't like that, you could think of 5 halves is going to get divided by x plus 3. So 5 halves is going to get multiplied by 1 over x plus 3. So 5 is going to be over 2 x plus 3. Another way that people do it is 5 over 2 all over x plus 3 over 1. Some people do this trick. That's the top. 5, that's the bottom, 2 times x plus 3. There's lots of ways for complex fractions. I'm just trying to stay consistent with my way. This would be the final partial fractions. Now, before I take any questions, can we go back to the one we just did with the thumb trick? Sorry, this is the thumb trick that we did the long way, and double check it. So this was the guy we were doing, right? X plus 7 over x minus 3 and x plus 2. Let's do it with the thumb trick way. So, x plus 7 all over. We still need to factor, or else we won't be able to do the thumb trick way. But I know what I need. Somebody, x minus 3. Somebody, x plus 2. Okay. If I'm covering x minus 3, who am I plugging in?
3.
Plug it in. 3 plus 7?
10.
3 plus 2?
5.
10 over 5?
2. That's crazy. That's so silly.
Cover! Plug in.
Negative 2.
Negative 2 plus 7. Negative 2 minus 3. 5 over negative 5.
Negative 1. Definitely which one?
But it only works on the easy ones, where we only have non-repeated linear factors. Meaning, we can't have an x minus 3 and another x minus 3. Can't have it squared. Can't have it cubed. Can't have it quadratic. But it's really nice for the easy ones. So we understand the thumb trick. What is it basically doing? Well, I'll show you what it's basically doing in just a second. I've kind of hinted at it though. No thumb trick on this one. Well, we can't even start with the thumb trick yet.
What happened?
Guys, divide first! Oh, you should have seen it, because the top wins, right? Okay, polynomial, long division. I'm going to go ahead and do it on a separate page just to keep it all nice and, well, I'll do it off to the side. Can I do that? Okay, off to the side, I'm going to do it in green, just because. So I have x to the 4th. Do you guys see why I did not show synthetic division? Does synthetic division let me divide by a cubic? No. It's not synthetic division. Polynomial. I don't think I need to leave any 0 placeholders. No, I'm good. How many times does x cubed go into x to the 4th?
X.
1x times, right? Division says I have to, well, if it's a polynomial, don't I have to distribute? So x times x cubed is x to the 4th. X times 2x squared is 2x cubed. X times x is x squared. This is division, so what do I have to do? Subtract. We're horrible. Just kidding, we make mistakes. Right? The sooner you admit that to yourself, the easier life will be. Distribute those negatives. That was life lesson. Now what?
5x squared.
Cancel? Cancel? 5x squared. Can't I rewrite stuff?
Yes.
Yay! Oh. Does anything else go in? Nope, now he's smaller. Which means this is my remainder. Which means he gets written on top of the original denominator. Well, I made him a little bit easier. I can rewrite this whole shebang as x plus 5x squared plus 20x plus 6 all over x times x squared plus 2x plus 1. I factored an x out. Is that okay?
Yes.
Ooh, can I factor more? Can't I make it x plus 1 times x plus 1? I wish I could do the thumb trick. They're all linear. That's good, but the problem is, are they all distinct? Ooh, struggle. Distinct means different from each other. Nope, I have a repeated linear factor.
No.
So, we gotta go back to the old-fashioned one. But maybe, I can show you a little trick along the way that has to do with the thumb trick. Just can't totally get us to the right answer, which is why we might have to do it using where the thumb trick came from. Now, quick word to the wise. You guys realize that x plus in the very, very front is pretty stinking important, right? Okay. That x plus made all the difference to take that whole nasty thing into this piece. So what I'm going to do right now is literally highlight this guy and say, you know what, he's my fraction. I'm going to take him off to the side and say, I need to cut you into partials. So I'm taking this guy and taking him off to the side. He's the guy I need to cut into partials. So 5x squared plus 20x plus 6 all over x times x plus 1 times x plus 1. You could write it as a squared. I'm just going to write them separate for a reason. There is something unique, and I think it was in that big old paragraph that we wrote down. There is something unique when we have repeated factors. We do need to make 3 different partial fractions, but it's not exactly the 3 that you would probably expect.
What?
Because if I did 2x plus 1s, that could just combine to be one fraction, no big deal. But the problem is, I could have gotten this fraction from x alone, x plus 1 alone, or x plus 1 squared. Technically, this guy could get multiplied by that to be that denominator. This could get multiplied by himself and that to get that denominator. And this could be multiplied by that to get that denominator. All 3 of these could go into that denominator. Now, the nice thing is, still linear, still linear, still linear, in the sense of the inside factor. We only need to change the letter on top if the inside is irreducible, could not be factored down anymore. So we still just keep it a constant C. All right. That was how to make the partials. Something new, something unique to repeated linear factors. Okay. Let's try to go back before the thumb trick. What would I do to both sides? Multiply by the common denominator. So I'm going to multiply both sides by this x times x plus 1 squared. We cancel all of those guys out. But what I do to one, I have to do to all. Some of you might just want to write it once and then think about the distribution. Just be careful. You have to make sure that you realize this needs to go to every single one. X cancels with the x. The x plus 1 cancels with one of the x plus 1s. The x plus 1 squared cancels with all of the x plus 1 squared. So that what I get is 5x squared plus 20x plus 6 equals a times x plus 1 squared plus b x times x plus 1 plus c x. Pause. If we were to totally go back to the very first way we solved, I would have to say, how many unknowns do I have? 3. Ooh, so how many equations do I need? How many different types of terms do I have? Not 2.
3
Why?
squared.
I have a squared term, an x squared. I have a x single term, and I have a constant term. Couldn't I say, let's gather all the x squareds? Couldn't I say, let's gather all the x's? And couldn't I say, let's gather all the constants? Would that get me 3 different lines?
Yeah.
With 3 different equations? With 3 different unknowns? So how fun does it sound solving a system of 3 equations with 3 unknowns? How much fun did we have in section 7.3? If there is another shortcut, would we like to try to use it? So instead of saying, hey, let's do the x squared terms, let's do the x terms, and let's do the constants, let's use the Heaviside trick. In the Heaviside trick, wasn't it all about plugging in zeros of the factors? Now, I can't do the cover up and have it perfectly get there. It won't work. But what I could do is say, well, but I do have factors with zeros. Wouldn't the 0 of this guy be 0? Let's say, okay, we're going to plug in x is 0 and see what happens. And what would be the 0 of these guys? So we're going to plug in -1 and see what happens. We can't exactly do the cover-up trick, but we can still plug in 0 and see what happens. And when we plug into every single x step. Mental mathers? You have to hope that this could be a shortcut to the whole system of 3 equations thing. If we plug in 0, 0 plus 0 plus 6. 6 equals. If I plug in 0, 1 squared times a is going to be 1a. If I plug in 0,
1
0 times 1 times b, but 0. If I plug in 0, yes. So what do I already know? I got one. So guess what I can do once I have one? Let's go say, you know what, from now on, let's make you 6. Is that okay? Okay. Now let's go plug in -1. Okay. If I plug in -1 squared, 1, okay, 5, right? Minus 20 plus 6. Is that okay? Over here. When I plug in -1, oh, well, -1 squared times 6 is just 0, right? 0.
Oh.
-1, 0. -1 times c. Plugging in -1 for all my x's. So -c is equal to, hold on, 5 minus 20 is -15. -15 plus 6 is -9. If -9 equals -c, then I know c equals 9. Aha! All right, let's go take them.
One more.
Oh, but guys, do I have any more zeros?
Plug in everything.
I can plug in any x I want to. I just plugged in the zeros because it cancels out stuff and makes life easier. So if we're out of zeros, plug in something else easy. Would be something else? Yeah, why not +1? It's not a 0, but oh well. Just down to 1 more. Just gotta plug in 1 more x. You can plug in 100 if you want, but you gross. Who wants to do that?
-0.
So plugging in -0. That's not gonna help so good. Or so well. X equals +1. All right. That's 5 plus 20 plus 6, right? Thomas has already gotten 31. And I agree. Other side. 1. We gotta plug in 1. 1 plus 1 is 2. 2 squared is 4. 4 times 6 is 24. 1 times b is b times 1 plus 1 is 2. 2b, right?
Or not.
That's next year. Oh, maybe in a couple years.
Nine.
Plug in 1. 1 times 9 is? Am I going to get there? Yeah, I am. But what did I avoid? A system of 3 equations. And that's even, we couldn't have even gotten that system of 3 equations until we FOILed and simplified everything. 24 and 9 is 33. 31 minus 33 is negative 2. So b is equal to, even though the thumb trick doesn't always work, we don't even need to plug that guy in. We have all 3 of our answers. Even though the thumb trick itself doesn't always work, the idea of plugging in the zeros to simplify the math is kind of nice. And if you run out of zeros, what did we do? And what if we had 2 more unknowns? So we would have had to plug in 2 more, and then maybe do a little baby system of equations, substitution, elimination, something. But it would save us from having like a system of 4 or 5 or 6 equations. Guys, we're not exactly done yet. Hold on. We were supposed to rewrite this guy in terms of his partial fractions, right? Hold on. This guy, didn't we divide first?
Yeah.
So didn't we figure out it was x plus a fraction?
Yeah.
And now we took that fraction and split them up?
Yeah.
So to finally state them, don't I have to start with x plus? Does that make sense? Now I say x plus, okay, all the partials. A goes over, gotta look back at your pattern. A goes over x, so A is 6. Then I have b over x plus 1. Then I have c over x plus 1 squared.
This took us 20 minutes.
Is one problem? Nah. It took us a little while though. But I also had to teach you the trick, right? Now that you know it, maybe it'll go faster. And also I had to make sure everyone was keeping track of what we were doing. So if you just look up and randomly see magical numbers, you might have no clue what's going on. Why was this one rough? Long division. Factoring, splitting up. Ooh, repeated, not distinct. Plugging in zeros, but it sure made it easier. I promise, I promise, I promise. So, you don't have to write this unless you want to. You can see what this says. More detail, basically, on the tricks. Okay? For linear factors, can we try to plug in the zeros? Yeah. And if we run out of zeros, can we plug in other stuff too? Yes. That's why it says, then you can also substitute other convenient values of x. Other easy ones. Quadratic factors. Well, you know what? We haven't even seen quadratic factors yet, so let's not even write that down. Long story short from this entire page, I just want you guys to realize we can plug in zeros of factors. We can actually plug in when x equals not capital A, not capital B, not capital C. But we can plug in any x's you want. I just tell you zeros are a really good idea. Does that make sense? Okay. So what gets different for... Okay. Basically the last one. It could be something else just nasty. Oh yeah. Hey look, he's just hanging out. This is basically our last one though. What do we do when we get quadratic factors? You might be like, I don't get it. We've had quadratics, then we've factored them. First of all, do I divide? Yes or no? No. No. Bottom ones. So I rewrite them. Factor in the denominator. Are you guys seeing to pull out that common x? I have x squared plus 4 remaining, yeah? Keep factoring! Killing stuff.
Puppies.
If that was a minus, we could do x plus 2, x minus 2.
Is there an I?
We're not going to do imaginaries. Good idea, though. Could make it x plus 2i, x minus 2i, but not imaginary. So therefore, we're stuck. And this is what I call an irreducible quadratic factor. But check out what changes. I still make a partial for each one. I still put an a. But what's different, almost, it's not b squared. We wrote this earlier.
Let's see.
Yeah. The linear The numerator needed to be 1 degree less, which would be a constant. The quadratic, I need it to be 1 degree less, which will be a linear. But then guess what? Multiply both sides by the common denominator. Thumb trick. No. You got a quadratic irreducible. No, 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 no. But I can do my trick of multiplying both sides by this guy. What do I do to one side? I do to the other. And all the terms of the other. If you need to write it, make it clear in your brain as to what to do, do it. What's left? This guy. How many different unknowns do we have? How many types of terms do we have? Could we have the x squared terms make a line? Have the x terms make a line? Have the constant terms make a line? Could we try to plug in zeros? What do you want to do?
Plug in the zeros.
Okay. Someone tell me a zero.
2. Oh wait, -2. Wait, oh, zero. That one doesn't make it 1.
Only
2i.
let's not plug in 2i. Let's plug in 0, and then let's say other convenient values. Do you guys realize we have to do this 3 times because we have 3 unknowns? How about x equals -1, x equals +1? They're not zeros, but oh well, easy. If I plug in 0, 0, 4, right? Plug in 0, 0, 4. Okay, plug in 0 over here. 0 squared plus 4 is 4a. And then plug in 0 here. Okay, remember, nice thing of zeros is they usually get an answer. Ha! What am I going to do with them? I still have 2 unknowns. Alright. -1 squared. +1. 3. -4 plus 4. When I plug in a -1. When I go to the other side, no one's going to cancel out, but I know that that's 1, so -1 squared is 1. 5 times 1 is 5. -b plus c times -1. That leads me to, well, 3 minus 4 is -1. 3. 3 minus 5 is -2. Plus, oh, that's not going to work. That's times, huh? Careful. Okay, so maybe we better stick it here. So -1, 3, 3 minus, okay, so -2 equals b minus c.
Are we going to do it from next one?
Gotta get us another equation. That wasn't enough to get an answer. But I bet if we do it one more time, we'll have a little baby system to solve. Plugging in +1. 3 plus 4 plus 4. +1. It's going to be 5a. Nope, sorry, 5 times 1. And then b plus c times 1. Oh, can't I just subtract the 5? So that's going to be 6 equals b plus c. Hey. What can I do?
Elimination. 2b equals.
Yeah, you guys just going to add down because the c's cancel? So 2b is equal to 4. So b is equal to 2. Ah! And then can't I back substitute again? Let's just go right back here. Say, well, fine. If b equals 2, then 6 equals 2 plus c. C is equal to, I think, +4. Anybody double checking?
Yeah.
Yes. Ha! So I can say the very end over x squared plus 4. A is equal to 1. B is equal to 2, and that was times an x plus c. Done. You're done. Woo! 10 seconds to spare. You're welcome. Section 7.4, partial fractions due tomorrow. Test corrections, let's just say by the end of the week. No, wait. End of the green and green this week. Wednesday. It'll be like with the homework, so we'll say do Wednesday test questions. Right. As far as the deadline and
Dude, I got Mr. Strike right now. I love him. Dude, I love his class. I want to sit there. Then I got Mother Hill after that. Guess what? I'm reading it. She's gonna wreck me. Mrs. Hill, I had to print something for her, but the printer's upstairs not working. So I'm gonna blame the school, and then she'll like be like, defy the patriarchy, you know? Something.
it doesn't work. I don't like after I still want to paper. We'll see how it goes. What are you two doing?
Reeves, I wait.